Building an agent means making dozens of design decisions with no obvious right answer. Which model to use, which tools to expose, how memory should work, what guardrails to add. This is about how to stop guessing and start measuring. We'll build a complete evaluation system across 3 levels: where to test, how to judge, and what to do with the results once you have them. Here's the mental model that shapes everything else. If an agent scores poorly, the first question isn't, do we need a better model? It's, is this a model problem or a harness problem? The harness is everything around the model: the prompts, the tools, the feedback loops, the constraints. The same model can perform very differently depending on how well that harness is built. One way to tell them apart is the model swap experiment. Keep the harness fixed and change only the model. If a stronger model barely moves the score, you've found a harness bug, not a capability gap. If a weaker model tanks the score, the model itself is likely the bottleneck. This is different from an ablation test, which disables one harness component at a time to isolate its contribution. Model swap tells you whether to blame the model or the harness. Ablation tells you which part of the harness matters. Let's see evaluation in action with a concrete example. A customer wants headphones refunded 3 days after purchase, and the policy allows a full refund within 7 days. The agent queries the order, checks the policy, processes the refund, and replies to the customer. We score that trajectory across 4 dimensions: operational correctness, policy compliance, information completeness, and hallucination. Notice that hallucination isn't graded on a scale, it's a veto item. A fluent, well-formatted answer full of fabricated facts is worse than a blunt but accurate one, so any hallucination zeroes out the whole score, no matter how well everything else performed. And a good evaluation doesn't stop at the easy case. It also tests what happens when the return request comes 15 days late, or when a customer claims a refund was already approved by someone else. Those boundary cases are what separate strong agents from weak ones. Everything that follows fits into 3 levels. First, the evaluation environment, where testing happens. Second, evaluation methods, how judgments get made, from datasets to metrics to automated judges to pairwise comparison. Third, evaluation-driven decisions, what to actually do with the results, including model selection and the statistical rigor needed to trust a conclusion. The thread connecting all 3. The real value of an evaluation system isn't scoring today's agent. It's letting you keep pace with how fast models are evolving. When a stronger or cheaper model ships, a team with solid evaluation infrastructure can make the switch decision in hours. A team without one is just guessing. Every evaluation environment is built from 5 pieces. The dataset defines the tasks, the initial state, and the goal. The environment state has to balance authenticity, following real business logic, like a refund never exceeding the original order amount, with controllability, meaning it can be reset to the exact same starting point every time. Tools should be atomic operations, never a single shortcut like solve the user's problem. Forcing the agent to combine query, verify, and act is what actually tests planning and reasoning. The rubric quantifies performance, whether binary, continuous, or multidimensional. And the interaction protocol defines how an episode starts, proceeds, and ends. When a task success is objectively checkable, did the test pass? Does the answer match? You don't need a human or an automated judge at all. For these tool calling scenarios, environments are typically layered by complexity. A single-turn environment fits simple questions with a direct answer. A tool environment supports multi-turn tool calls, like searching several pages and synthesizing a result. A stateful tool environment adds persistent state for tasks like modifying database records. And a sandboxed environment adds full isolation for things like running and testing code. Pick the simplest one that fits the task. Don't reach for a sandboxed. stateful environment to evaluate a single math question. Most benchmarks hand the agent the full problem statement right away. Real conversations don't work that way. Someone says, the internet isn't working, and the agent has to ask the right questions to figure out what's actually wrong. That clarifying behavior is itself a capability being tested. The solution many evaluation frameworks use is a simulated user. Another language model plays the role of the user, following a fixed script. It knows the full situation in advance, but only reveals pieces of it as the conversation naturally calls for them, staying reproducible because the script never changes, while still feeling like a real, sometimes vague, sometimes emotional human on the other end. Early evaluation of these conversational scenarios checks two things. Did the underlying system end up in the right state? And did the agent actually communicate the important details to the user? But scoring is often all or nothing. Miss one small detail, and you score the same zero as a complete failure. More advanced versions of this approach add a dual control environment, where the simulated user can also take actions in the shared environment. For example, actually switching their phone to airplane mode when the agent tells them to. That's much closer to real technical support, where you need the human on the other end to actually do something too. These frameworks also tighten task generation, so success conditions are less ambiguous. Designing the dataset is where most of the real evaluation work lives. 5 tensions come up again and again. First, clarity versus openness. Descriptions need to be clear enough to score reliably, but open enough that they don't stifle creative problem solving. Second, authenticity versus controllability. Real-world data is messy. So many teams start with raw examples and then curate a verified, high-quality subset. Third, diversity versus systematization. Tasks need to be tagged by the capability they test, so results reveal a profile of strengths and weaknesses, not just one number. Fourth, cost versus coverage. Bigger datasets cost more to run, so teams often trade dataset size for stricter quality control. Fifth, and often the most overlooked, preventing data contamination. If an evaluation task leaked into a model's training data, you're measuring memorization, not ability, like scoring well on an exam because you memorized the answer key. Some frameworks embed unique tracking identifiers into tasks, so if a model ever reproduces one verbatim, you know it memorized the benchmark rather than solved it. A well-tiered dataset doesn't just give you one success rate, it tells you where to invest engineering effort. Tasks that need only 1 or 2 tool calls test basic execution. Tasks that require multi-step reasoning test planning. Tasks that require complex combinations of both test long-horizon reasoning and architecture. If an agent fails the simple tier, that's a prompting problem. If it fails the hardest tier, you likely need a better planning architecture altogether. On verification, the gold standard is checking things an agent can't fake. Beyond just running a new test, the strongest approaches also rerun all the old tests to make sure nothing else broke. Some go even further. Connecting directly to a database or inspecting a web page's structure to catch situations where something looked done on the surface but wasn't actually completed underneath. Outcome alone tells you what happened. Process metrics tell you how well. Action legality rate measures whether every operation the agent took was valid and authorized. Tool call correctness goes a step further, checking whether the parameters passed to each tool actually make sense for the situation, not just whether they're syntactically valid. Path efficiency looks at the number of steps taken, how many were redundant, and how often the agent backtracked to fix its own mistakes. Some backtracking is healthy self-correction. Frequent backtracking is a sign of weak forward planning. Retrieval coverage checks whether an agent explored enough of the available information or stopped at the first page of results. And cost and latency track requests, tokens, and wall clock time throughout the whole process. This is one of the most commonly confused pairs of metrics, and confusing it leads to real mistakes. Pass at K measures the probability that at least one of K attempts succeeds. It answers, can the agent do this at all? Pass to the power of K measures the probability that all K attempts succeed. It answers, is the agent reliable? Best at K measures the quality of the single best attempt out of K. Useful for open-ended tasks with continuous scoring rather than pass or fail. Here's why the distinction matters. If a single attempt succeeds 60% of the time, then across 5 attempts, the probability of succeeding at least once is about 99%, nearly certain. But the probability of succeeding all 5 times is only about 8%, quite unlikely. Same underlying agent, wildly different numbers, depending on which question you're actually asking. Use the wrong one, and you'll draw the wrong conclusion about whether the system is ready. Safety follows the same zero-tolerance logic as hallucination. One serious violation vetoes the whole evaluation, and it doesn't get averaged out by good performance elsewhere. Robustness measures how stable an agent is under uncertainty. Does its behavior swing wildly with different random seeds? Does it break when a website's layout changes? Can it gracefully handle a slow or failing API call? And does old, outdated information sitting in its memory ever lead it to a wrong decision? There's also a subtle but important distinction between trajectory and outcome. Trajectory is what the agent said and did along the way, for example, announcing that a booking is complete. Outcome is what's actually true afterward. Is there really a record in the system? A flight booking agent once found a loophole in an airline's policy and got the customer a cheaper fare by deviating from the expected path. Judge that run only against the expected script, and it looks like a failure. Judge it by the actual outcome, and it's a win. You need both lenses, or you'll miss either said it but didn't do it, or genuinely creative problem solving that got a better result. Open-ended tasks, writing a report, handling a complaint, generating creative content, don't have one single correct answer, so a language model acting as a judge is often the only way to evaluate them at scale. But judges carry biases. The most common is length bias, a tendency to score longer, more detailed answers higher, even when they aren't actually more correct. Guard against that by capping response length in the scoring criteria, comparing answers of similar length in head-to-head tests, and regularly checking whether high scores just track word count. Good scoring criteria follow 4 principles. They're grounded in real domain expertise, not generic writing quality. They cover the full picture, including common pitfalls and failure modes explicitly. They're weighted by importance, with certain items acting as automatic vetoes, and every scoring level is objectively verifiable. Never something vague like demonstrates deep understanding, but instead something checkable, like cites 2 authoritative sources and explains how they support the conclusion. Here's what well-designed scoring criteria look like in practice. Take a memory question like, who is my daughter's pediatrician? Where the answer requires linking 2 separate pieces of information from 2 different conversations. The scoring dimensions are factual correctness, information completeness, reasoning correctness, and hallucination as a veto. Each score level describes a specific checkable behavior rather than a vague adjective. For example, correctly answers the doctor's name and explicitly links it back to the daughter earns the top score. Edge cases get written down in advance too, so a judge isn't improvising when it hits an ambiguous situation, like a family with 2 daughters who see different doctors. Run criteria like this across dozens of test cases, and a low average score on one dimension, say, linking information across conversations, tells you exactly where the underlying system is weak. If an agent is evaluated by a judge from the exact same model family it's built on, it can quietly learn to exploit that specific judge's blind spots and get away with it. because the same blind spot that created the exploit also hides it. The moment a score becomes an optimization target, it stops being a trustworthy measure. The fix is to use multiple, independent judges from different model families. Their biases rarely line up the same way, so an agent can rarely fool all of them at once. A related problem shows up in head-to-head comparisons. Judges tend to favor whichever answer appears first, regardless of actual quality. The fix there is to judge every pair twice, with the order swapped each time, and either average the results or discard cases where the two judgments disagree. This kind of automated judging also extends beyond text, evaluating synthesized speech for naturalness, transcription for meaning-changing errors, visual interfaces through one model proposing a design and another reviewing it, and video edits through keyframe checks. Sometimes the real question isn't how good is this agent on an absolute scale, but is option A better than option B? A rating system built on repeated head-to-head matchups answers that directly. The same approach chess uses to rank players. Each win or loss updates a relative strength score, with upsets producing bigger swings so rankings converge quickly toward the truth. Large-scale platforms run this with real users making blind, anonymous choices between two responses, which has one big advantage. No absolute standard needs to be defined in advance. The trade-off is that rankings only reflect whatever questions people happen to ask. If a flood of users ask programming questions, models strong at programming will rank higher, which may say very little about their skill elsewhere. It's also worth knowing that this same which is better comparison signal doesn't stay confined to evaluation. Some of the most efficient training methods today reuse exactly this kind of relative comparison as a training signal, skipping a separate value estimation step entirely. Two numbers get conflated constantly: how quickly the first token of a response appears, and how fast tokens stream out after that. They come from two different stages of the underlying computation and two different bottlenecks, one dominated by processing the input, the other by generating output token by token. And don't just look at average latency. The 95th percentile matters more because that's what your unluckiest users actually experience, and averages can hide serious slowdowns affecting a minority. On cost, the trap is judging a model's price tag in isolation. A cheap model with a low success rate can end up costing more overall once you count the retries needed to get a correct result. And the right success metric depends on the use case. For everyday tasks, look at single attempt success rate. For critical operations, prioritize the probability that every attempt succeeds. For exploratory tasks, look at the best possible outcome given multiple tries. Token pricing looks simple until you watch how a real multi-turn conversation grows. Every round resends the entire history, so the model has context, which means cost grows faster than linearly unless caching is used aggressively. Round 1 sends 1,000 tokens, round 2 sends 2,000, round 3 sends 3,000, and the total is far more than 3 times a single round. There are two amplifiers people often forget to budget for. One is thinking tokens, generated internally, never shown to the user, but still billed. The other is tool output. A single web search result might be a few thousand tokens, and once it's in the conversation, it gets rebilled as input on every single round afterward. The fix isn't simply picking a cheaper model. It's reusing cached context wherever possible, compressing history instead of letting it grow unchecked, and routing simple requests to lightweight models while reserving powerful ones for complex reasoning. Here's the reality check on everything before it. Say an evaluation of 100 cases shows a 70% success rate. The natural sampling error on that number is large enough that a true improvement could easily be anywhere within about 9 percentage points in either direction. A 3-point improvement between two configurations, something like 73% versus 70%, is entirely within that noise band. Deciding to switch systems on evidence that small is close to a coin flip. 2 habits fix this. Run each configuration multiple times and report both the average and the spread, because outputs aren't perfectly deterministic. And when comparing 2 configurations on the exact same set of tasks, use a paired analysis that looks only at the cases where the 2 disagree. It cancels out shared task difficulty noise and is far more sensitive than treating the 2 success rates as independent. One more trap: testing several hypotheses at once. Even at a 95% confidence threshold for each individual conclusion, testing 6 hypotheses in parallel gives you a real chance, over 1 in 4, that something looks significant purely by luck. You can't watch an agent think, so you reconstruct what happened from what it left behind, the same way a doctor reads vital signs instead of looking inside the body directly. The key idea is a trace and span structure. One full task execution is a trace, and every individual model call, tool call, or retrieval inside it is a span, all linked together into an execution tree. Standardized protocols let this data flow between different tools without lock-in. Modern observability platforms combine tracing, evaluation, and live experimentation into one loop, routing a portion of traffic to a new version and automatically comparing outcomes. But the most valuable use of this data isn't just debugging a single failure. It's taking real production traces, stripping out anything sensitive, and turning the failed or suspicious ones into new test cases. That way, an evaluation set stops being a static snapshot and keeps evolving alongside real user behavior. Here's the whole methodology applied to a real diagnostic case. The first rule when a score suddenly drops: check the evaluation system itself before touching the agent. A stale test environment or a bug in the scorer looks identical to a genuine regression in the headline number. Once the data is trustworthy, the diagnosis can begin. In one such case, routine tasks succeed nearly 100% of the time, while failures cluster tightly around a handful of areas: messaging, network settings, list queries, and playlist creation in a specialized app. On the surface, these look unrelated. Cross-referencing failures against the specific capability each task requires reveals the shared root causes. Struggles with extracting information from images, recognizing when a calculation is needed, and understanding non-standard interface layouts. From there, hypotheses get built in layers. Cheap, surface-level fixes first, like adding navigation hints. Then mid-level fixes, like repairing a broken data pipeline or selectively enabling deeper reasoning. And only then, deep and expensive fixes, like swapping in a stronger model or feeding it richer input. This is the discipline that separates real evaluation-driven engineering from just chasing whatever seems to help. Global changes that help on average aren't automatically worth deploying everywhere. In one case, turning on deeper reasoning across every task did improve overall performance slightly, but it turned out only a small fraction of tasks actually needed it. So tripling the cost and latency for every single task was the wrong trade. Compare 2 other fixes side by side. Swapping in a stronger model barely moved performance on a hard capability while more than tripling latency, but simply giving the same original model richer input information, without changing the model at all, nearly tripled success on that same capability for a fraction of the cost. The bottleneck wasn't reasoning ability, it was information. That's a conclusion you only reach by testing model strength and input richness independently, instead of assuming a stronger model is always the answer. Fixing the top few problems doesn't end the process. It reveals the next layer, and some of the new issues are side effects of the fixes themselves, like additional information in the input scattering the model's focus. This is why evaluation should run on a regular cadence rather than once before a launch. Each cycle both confirms that real progress happened and surfaces exactly what to attack next. That repeating cycle, diagnose, hypothesize, test, decide, repeat, is what turns agent development from trial and error into something closer to a genuinely scientific process. Everything up to this point evaluates a system from the outside. The most mature products go further and build evaluation directly into the product itself. One powerful pattern is a master switch that can independently disable any major feature: deeper reasoning, memory, background processing, context compression, creating a bare baseline to compare against. That answers a sharper question than, does this feature seem useful? Does it actually help measurably right now? Run that check regularly, ideally before every major release, and you'll sometimes find feature debt, a capability that mattered a while ago, but that a stronger underlying model has since made unnecessary. This kind of switch needs to be designed into the architecture from the very beginning, because retrofitting it later means untangling assumptions baked in everywhere. The other core practice is live experimentation, randomly splitting real users between an old and a new version and comparing outcomes on real behavior, not just offline test scores. If there's one idea to take away, it's this: an evaluation system isn't really about the score you get today. It's insurance for tomorrow, for the day a stronger or cheaper option becomes available. And you need to know, with real evidence rather than a public leaderboard, whether it's actually better for your specific use case. Evaluate the whole system, not just the model in isolation. Build scoring criteria around checkable behavior, not vague impressions. Match the metric to the actual question being asked. Stay skeptical of small differences until you've checked whether they're bigger than ordinary noise. Teams with this kind of infrastructure make high-stakes decisions in hours, backed by evidence. Everyone else is relying on intuition, in a field moving too fast for intuition alone to keep up.